I think this is on. Yes, it is on.
Okay. Time is running. Welcome to our afternoon session on machine learning in EDA, how it's used in research, in application industry to improve the design process, to come up with better results, to have results in a faster way. And it's a pleasure to introduce Andreas Gerstlauer. Andreas Gerstlauer studied in Germany, in Stuttgart, then went to Irvine, where we both know us from, made his PhD at Dengaiski, and now is professor at the Technical University in Texas at Austin. And I think I don't want to catch too much time.
No, that's
Andreas,
good enough.
the stage is yours.
Thank you. Yeah, so welcome to our special session. I'm going to have the first talk. We have in the schedule 4 talks listed, but one of the speakers is not able to make it, so he recorded a talk. I will share the link afterwards, but I don't think it makes sense to play back a recording, so we'll just send the link, and rather each of us have more time to present our parts of the talk. So let me start by giving my presentation. So we essentially have organized the special sessions along abstraction levels, so coming down from top down. So I'm going to talk about machine learning applications at the system level in particular, but I also want to give a little bit of an introduction about system level machine learning for electronic design automation, or for design processes more generally, and then what that means for the system level. And we'll have presentations going down at lower levels of abstractions. Again, Jiro Zhang's talk about HLS, which is being shared as a recording, and then talk about RTL, and then we have the industry perspective from Wolfgang at the very end. Okay, so why do we want to do machine learning, right? For the design process in general, and especially at a system level. Ultimately, that's all driven by the complexity challenges that we're facing today. Systems are becoming more complex, more heterogeneous. We have new implementation challenges that are cropping up from the bottom, which are driving these new levels of design problems and new co-design problems, right? When people talk about co-design, we can generally distinguish between, right, co-designing across different implementation options, ranging from CPUs at the system level to, right, novel quantum accelerators, neuromorphic accelerators. But co-design also means co-designing across abstraction levels, right? As I said, new design implementation challenges that are creeping up from the bottom that we should take into account as early as possible, right? And all of that creates huge design spaces, huge design problems, and our existing methods are running out of steam. We have scalability issues, so machine learning to the rescue, question mark, right? That's what it has brought a lot of innovations in other fields, right? What does that mean for embedded system design? What does it mean for chip design, SoC design, and so on, right? So if we look generally at the design process, right, we can generally say that what does it mean to design something, right? So designing something means that you make design decisions, then you have some way of evaluating the impact of those decisions, and then in return drives your next set of decisions that you make. This can be done either in a constructive way. You gradually assemble the system and make one decision, check its impact, right? Then make the next decision until you're done, or you have a complete system solution and you try to make iterative improvements on this process, right? And traditionally, right, so design is composed out of decision-making processes and modeling, right? Evaluating a decision that you've made, okay? And both of these are challenging to do. And the idea essentially, right, is that you apply ultimately machine learning to both of these topics, right? Or you can apply machine learning to both of these topics, okay? So a little bit a deeper dive into the design process. Like I said, you have a decision-making optimization algorithm. Traditionally, we use some form of heuristics, meta-heuristics for this. Then you produce a design representation, and then you have some way of modeling, analyzing the cost function, right? For this design representation, which in turn drives the next decision that you make, and all of this driven by constraints ultimately, right? We use for modeling often analytical models or simulation-based methods, and for optimization some form of heuristic traditionally. But the idea of machine learning is to replace potentially both of these aspects, right? On the modeling side, the idea of so-called predictive modeling. Predictive models, can you predict the performance and power of a design representation without having to go through the whole design process? And on the decision-making side, what people a lot of apply, and a lot of buzz is about applying reinforcement learning to this problem ultimately. So that's the idea, right? And I want to talk for the rest of this presentation, specifically what that means at a system level, what some people have done, what we've done in our group, but also like a little bit more general view on this. And then we'll have presentations about lower levels of abstraction later, right? So on the modeling side, right, at the system level, what do we want to model here? We want to model a complete system on chip implementation that consists of a heterogeneous set of processing elements ranging from programmable CPUs, GPUs to customized programmable processors, DSPs, and so on, all the way to full custom accelerators, together with the interconnect that puts all of this together. On top of that is running an application, right, on top of each of these processors as software, right, or as custom hardware functions implemented in an ASIC or FPGA technology. Traditionally, right, we do this often, we resort typically at this level, at the system level, to simulation-based modeling to get early performance and power estimates. So we have component models written in C, C++ languages or other ways, and then we have a modeling backplane, for example, something like System-C, where we combine different heterogeneous component models together and co-simulate the whole system on whole. There are analytical approaches to try to model something at this level, right? But there's limitations on what you can do, right? So yes, if we look at the modeling space, you can try to model this analytically, which is fast, but often inaccurate in capturing a lot of the dynamic effects that we have at this high abstraction level, at this complete as a system level. At the other end of the spectrum, we have simulation technologies, which, depending on the level of detail that you model your system, can be very accurate, but are slow, right? So there's this fundamental trade-off. And there's a trade-off between analytical and simulation-based modeling. And what we're hoping, obviously, is that with machine learning, that we can fill the gap between analytical and simulation-based modeling. Can we have a model that is as fast as an analytical approach while, right, being as accurate as a detailed simulation, ideally, right? Can we get the best of both worlds? And can we fill that gap through machine learning? So, okay, let me move here. So, right, some key principles, right, of applying machine learning to system level modeling. We spend a lot of effort on developing, and whole PhD theses have been written about how to write abstract models at the system level, the whole area of transaction level modeling, post-compiled simulation, and all these different techniques that try to push the accuracy speed trade-off out. But we spend a lot of manual effort on this. So the hope with machine learning, can we learn a model, a performance and power model, rather than having to manually construct it in a tedious fashion, right? Especially for every new component or every new system. And the other aspect potentially is, right, rather than simulating out the time horizon in painstaking detail, can we simulate potentially for a little bit and then predict out how the system would scale out, right, over time, right, ultimately. So predict rather than simulate in the time axis. And what typically people apply at this level is some form of supervised learning. So in machine learning terminology, this is often formulated as a supervised learning problem, okay? Supervised learning in the sense of you learn the low-level behavior, and then you make a model that can predict the low-level behavior from some high level of abstraction. And similarly, you learn on a short time period and predict out into the future, right? So that's the idea. So you can look at this as sort of trying to make models, right, that can predict across three different axes, ultimately. We want to be able to potentially predict, right, across the abstraction level, meaning, right, from a piece of C code, can I predict gate level power, for example, or gate level energy, or gate level performance, right? We want to be able to potentially predict across components, right? These are the two co-design axes that I presented earlier. Can I predict from running on the CPU, right, what will happen if I map it out to the GPU or to an accelerator, okay, to a different implementation choice. And then we also want to predict over time, right, cross-temporal, trying to predict the future ultimately, right, in the end, right? And we can apply machine learning techniques, right, to all of these problems in the end. So I want to just give a little bit of a flavor, right, what this looks like, especially at the system level. So at the system level, right, we typically try to construct a very high-level abstraction model at the C, C++ level that predicts, right, low-level implementation details. And traditionally, in the old days, what we did, we manually built abstractions, okay? Or we manually, right, measure things at the bottom and we back annotate them into the C code or do other mechanisms like that, potentially manually or semi-automated, right, in the end. And again, the whole premise of machine learning is rather than do this manually, can we automatically learn, right, the low-level representation and attach a machine learning model to C code to predict gate level, right, implementation details, okay, ultimately, right? So then to be able to predict down in the downward axis, right? So what does that mean, right? You can look at it, right? Traditionally, we have simulators and models, and simulation-based model has all of these levels of abstraction. So you can typically break a simulation down into the functional aspects, trying to simulate the input-output behavior and attaching a timing, power, performance model to the functional simulation, right, to predict, right, the corresponding perp metrics as I've outlaid here, right? And we have simulators at low levels of abstraction. We have manually constructed simulators at high levels of abstraction, right? And then the idea of machine learning is rather than manually constructing the top, right, we're trying to ultimately, right, learn, for example, a functional model from low-level simulations. So the idea is you run a few selected low-level simulations, and then you learn a model at the high level, and then you can apply new inputs to the high-level model and predict, right, what the outputs would have been of the low-level reference simulation. And you can do the same for timing behavior, right? Can we learn a timing model, right? We train it on a selected set of gate-level simulations. We train it to take features from a high-level C++ simulation, and then at the future, we run C++ simulation and we make predictions about what the gate-level power performance and power would have been, right? So that's the ultimate idea. Now, the reference here could be either an existing simulator, or it could be obviously running these on, right, real hardware and learning a model for real hardware from real hardware observations. Both of this is possible, right? So that's the idea of cross-layer prediction, right? Learn a high-level model that predicts, right, low-level implementation details from high-level observations, driven by very abstract high-level observations. The idea of cross-platform prediction is then once you have actually real hardware, right? The idea is essentially, right, rather than learning from the hardware, the same hardware that you're trying to build a model for, right? Can you run on a different target hardware, right? So you take a host hardware where you run an application on, you collect features on that, and can you train a model that predicts the behavior of that particular application on a completely different set of hardware, okay? We'll see examples of that later, but basically, can I run a piece of C code on an Intel processor and predict ARM performance and power? Or can I predict FPGA performance and power, okay? Or GPU performance and power? This is useful, right, for programmers or system designers, right? Before you implement it on a GPU, you want to predict whether it's worthwhile to moving the code to the GPU, for example, right? And other features like that, okay? So like I said, formulation-wise, this is typically formulated as a supervised learning formulation. So you have some high-level model, okay, where you execute maybe just functionally accurate, no information about timing, out of which you extract features in machine learning term. You have a reference execution where you have the accurate implementation of a particular, right, target. You run a certain set of micro benchmarks on both the high-level model to extract the features and the low-level reference implementation. You train an ML model such that during prediction time, all you need to do, right? I don't know if this works. All that you need to do is write a high-level model, extract the features, and predict the low-level, right, implementation details at a very abstract level of representation. And this can be applied now in different forms. I just want to give a few examples. This is some work that we did on developing power models, especially at the high level. So we did some work on microarchitecture level power modeling and source level power modeling, but basically the idea is very similar. Here, in this case, the reference is a gate level netlist of your particular target. You run gate level simulation, you get gate level reference power, and then you have some high level C++ model out of which you extract activity. You train a machine learning model such that at prediction time, you just run the C++ simulation and can predict gate level power, okay, at a very high level of accuracy. Then the question is just, right, what is the high level representation? What are the features? At the microarchitecture level, we assume that you have a typical microarchitecture simulator, which is cycle accurate and microarchitecture level accurate. We're able to extract input-output relationships at the level of microarchitectural blocks. and we use that to predict gate level cycle accurate power down to a very high level of accuracy. Okay, so we collect features from the microarchitecture simulation. We train, right, a machine learning model on these features to predict gate level power, right? And we can do that then at a very fine temporal and spatial granularity. The key is here, right, in terms of machine learning models that we apply to this work is that we used advanced nonlinear regressors, okay? There's been a lot of work on using linear models for power modeling, but this problem is inherently nonlinear. At the same time, we cannot apply deep learning to this problem because we don't have the training data. Collecting the training data is expensive because we need to run gate level simulations, okay? If that time takes as long as running the application in the first place, there's no point in building a model, okay? So we need to have, right, there's other things other than deep learning, right? And that's some aspect that I want to take away from this presentation. You can then do similar things at the source level where the input is not a microarchitectural simulation, but actually just a C execution of the functional behavior of the algorithm that you want to run. In this case, we need to annotate the C code with a little bit of information to extract activity information from it. Okay, and then we can drive again a power model, right, with this, and depending at level of detail or insight you have, right, you can extend how much information you can track. At the minimum, you just track the inputs and outputs to every function. At the most detailed level, you track exactly what data is flowing through which operand and each operation in the C code. And then you can build power models at the invocation level, block level, or cycle down to the cycle level and make predictions of this, right? And again, with, right, very good accuracy and very fast speed. And again, right, being able to train these models with very few test vectors to make predictions. Okay. All right. So that's examples of cross-layer prediction. Again, taking the same idea, but then applying it to cross-platform prediction. The only difference is that you now, right, replace the target not with a gate level simulation, but by running it on a completely different processor. Okay. So the host in this case, for example, is an x86 machine. The target is a reference simulation of an ARM processor. This could be running on a real ARM as long as you have the capability to measure performance and power in some way. You train the model to correlate the two for a set of micro benchmarks, and then you can run whole applications later on the x86 host and predict ARM performance and power, okay, very accurately. And the thing that we can leverage here, right? So this has been done for many different combinations, predicting from one CPU to another. That's what we've done. Other people have done GPU to GPU predictions or CPU to FPGA predictions, for example, right? Predicting across different implementation targets. So the one thing you can leverage today is that we have information on most existing simulation hosts. There's hardware counters that are available inside the microarchitecture that give us actually very detailed insights how an application runs in a microarchitecture. We can use these hardware counters on the x86 host as features for the prediction. And then the reference is just target performance and power, ARM performance and power. And again, we train a model. And again, we need to use relatively lightweight models because we want to be able to train quickly and make fast predictions. In this case, what we applied is a locally linear, piecewise linear lasso regression in this example, okay? Again, the problem is nonlinear. You cannot do globally linear, but you can at least do piecewise linear approximations. And you do that at program phase level. And again, we can do that either instrumentation-based, where you instrument the source code, compile it to x86, run it, or you can do it completely transparently. You can do it for arbitrary binaries by you setting up a timer interrupt to collect hardware counters at regular intervals, and then make the predictions. And then you see some sort of typical accuracy and speed numbers. The accuracy and speed depends on the granularity at which you make predictions and the granularity at which you collect host counters. That determines the overhead, right? And that determines the accuracy. The finer the granularity, the more data you have, but then you have alignment problems and other things that come into play. But the key aspect is that you can potentially now predict ARM performance and power faster than running on the ARM itself, by simply running on an x86 host that is orders of magnitude potentially faster, right? We can make predictions for a target, right? So we can predict ARM executions from x86 executions and train a model to do that, right? Okay. Last piece, the third axis of modeling and where we apply machine learning is the cross-temporal prediction. This is the classic problem, right, of essentially trying to predict the future, okay, the future behavior or workload. Where is this useful? This is useful, for example, for runtime systems to make predictions about the future. Most power management and other techniques are often just reactive. They react to changes in the system. If you can predict a change coming up in the system, you can make changes to task mapping, cache configurations, or other things much earlier, right? In the end. The key to recognize is that, ultimately workloads go through repeated patterns of execution because our code is driven by loops, okay? Loop structures. So there's repeated executions, and there's a hope that we can learn these patterns and predict them out, right? But we have to obviously take into account that there's short-term patterns, mid-term patterns, and long-term patterns. So we've looked at this problem in various dimensions, right? Short-term forecasting, long-term forecasting. In the long-term level, what you basically try to look at is the phase behavior of workloads, right? Workloads are going to stable phases, right? Where you're in a certain loop structure, then you go to another phase, right? And you try to learn and predict the phase patterns, right? So the short-term forecasting problem is a classic machine learning problem. It's a time series forecasting, not different than forecasting stock prices, for example, or other things, right? And a lot of work has happened on this, right? LSTMs, recurrent neural networks, are sort of the classical methods, but there's new methods in this area. For long-term forecasting, we have two problems. We need to first detect phases in the execution. That's an unsupervised classification problem, or usually phrased as an unsupervised classification problem. And then we need to, out of the phase patterns, make a prediction, which is again, a time series forecasting problem. So different applications of various ML algorithms, right? So we've done some work on this space too in our group, right? So for the short-term forecasting, you can use SVM or LSTM regressors. There's new work in the time series domain, things like matrix profiles. And then you can compare this. What we did is try to make basically forecasting models that are phase aware. Rather than try to learn a global model that predicts out the next 20 samples, you learn a model that's specific to each phase of the workload. And that can make the model more accurate, right? Because the model is now specific to a certain region in the workload and predicting the behavior there. And then for the long-term forecasting, like I said, that's a question of phase classification and prediction, but you see sort of, what the model can predict. And there's different ways you can predict. Just again, predicting in the next 20 time steps, will there be a phase change? Or trying to predict out even when will the next phase change be and when will what will the other phase be, right? Even predicting out to a more coarser grained time horizon. And again, these types of models are useful for runtime systems. So we're currently applying them to cache configurations, to task mapping problems at runtime, right? Again, if you know what's coming in the future, you can make better decisions. That's the ultimate idea here, right? So some challenges, right? I mentioned some of this already here. We have to be careful about the overhead to collect training information. If you have a gate level reference simulation that you need to run, the training samples don't come for free. They have to be painfully collected, okay? At the same time, if you want to deploy the model at runtime, you need to care about model complexity, okay? For both of these reasons, deep learning is often not an option, or that's very much questionable. Right? It has high complexity, deployment inference complexity has high training complexity. So what we've worked on, and what I think my point is, that we need to think about dedicated domain-specific learning formulations for the problem at hand, okay? In particular, deep learning is always, I call it machine learning for dummies. You try to recover basically everything from raw data. We know a lot of things about design already as humans. We traditionally encode that as heuristics. Here we can encode it as feature selection. There's a lot of intelligence that you can apply in feature selection, which then makes what you need to learn much simpler, okay? And we can apply other machine learning formulations. There's other learnings other than deep learning. And especially when it comes to learning nonlinear relationships, there has been a lot of advances in ML, in the ML domain there too, right? Another question is, what's an optimal training set? Again, because training is so expensive, you want to have ideal, optimally coverage of your training space. Where do the training data come from? Traditionally, you just run some micro benchmarks, but do the micro benchmarks capture all possible behaviors in an optimal way? Can you synthesize an optimal training set, right? These types of questions. And again, for most of these approaches, you still need an accurate reference model. You still need to have a low-level, gate-level simulation, other things, right? That you can fall back to, right? Okay, a few words about optimization. Again, right? Applying it to modeling and applying it to optimization. So coming back to the design flow, what does optimization mean at the system level? At the system level, we typically try to solve the mapping problem. That means coming up with an SoC architecture, allocating heterogeneous components, connecting them, mapping the tasks of some application description onto the SoC platform, right? And then potentially scheduling tasks if they're running on sequential processors, right? Traditionally, we either use heuristics. For example, variants of list schedulers are widely used to solve the task mapping problem. Traditional heuristics are limited, right? They often make very simplifying assumptions about either the application or the architecture model. The de facto standard at the system level is to use meta heuristics like simulated annealing or evolutionary algorithms for this problem. Some people call evolutionary algorithm machine learning. I don't. This is still an intelligent search algorithm. It's not machine learning. There's nothing learned, right? In particular, you cannot take one evolutionary algorithm execution and apply it to the next problem, and it will not retain anything. It has not learned anything, right? You rediscover this design space every single time, okay? So that's not machine learning. So how do you apply machine learning to optimization problems? Okay, the standard way to do is using some form of so-called reinforcement learning. For those of you that are familiar or not familiar, right? This is the canonical picture of what reinforcement learning looks like. You have some sort of intelligent agent, right? That takes actions on the environment. This is often coming from robotics, right? The environment, this would be a robot, right? That it makes actions and then that changes the state of the environment and you get a particular notion of a reward. Are you getting closer to your target? Okay, all right. This has been applied, right? Obviously in robotics, it has also been applied to play games, right? AlphaGo and all these other game playing agents are usually modeled as reinforcement learning, right? Formulations, okay? In a gameplay, the action is, right, making a move on a chessboard, for example. The environment is the board, that's the current state. And the reward is, right, how you closer to winning, basically, the game. So what does that mean for design? For design, right, the decision-making part is now becoming the agent, the RL agent, okay? We takes actions. The actions are design decisions. The environment is a representation of the design, which is also like the state. And then we have the reward function that basically takes the current design representation and translates it into a reward. For us, the reward is timing, performance, power. So the models that I just talked about are the reward functions in the RL loop, basically, right? So, and again, we can apply ML to both. We talked already about, right? For us at the system level, computing the reward is non-trivial, okay? For a robot, the reward may be easy. You're closer to the target. That may be easy to estimate. For us, estimating the timing and performance, right, of a design representation is complicated. And for gameplay, the same, right? Estimating from the current state of a chessboard whether you're winning or not is non-trivial. And people have applied in these game-playing robots deep neural networks to make that estimation. Take a picture of the chessboard, estimate, am I winning or not, right? The likelihood of winning, right? We talked about this already, right? And then the other question is, right, what does the agent looks like? And then people just apply standard RL formulations, okay? This has been successfully done at the physical design level. There's a lot of traction there that people have used RL agents to do floor planning and other things, but the work at system level is much more limited. And I just want to give some examples of work that I know of, right? You can again formulate this as a constructive problem. In the constructive case, your design representation is a partial architecture representation. And then, right, you make gradually decisions of allocating more and more components, right? And you go through this process. This particular work used the so-called Monte Carlo tree search algorithm to apply to this problem. This is a design time problem. And the reward functions, they either use simulation or some neural network to predict latency and power in this case, right? Again, a design time problem. You can also formulate this as iteratively, in which case you have a complete solution at every point of time. The advantage is if you do it iteratively, you can also apply it online at runtime now, right? You're making moves, okay? You make changes to an existing system, right? To improve, for example, certain behavior. In this case, this was for thermal aware task mapping. So the decisions are task to core assignments. We can measure the actual temperature from the hardware that we're running on, right? And then the reward is how far are you away from a critical temperature, right? Okay, and that's what you're trying to optimize. And in this case, they use a formulation called Q-learning, which is another machine learning, traditional machine learning formulation. So I don't want to go into details of all of this, right? Just want to give you a flavor, and that basically wraps up my discussion, right? Mainly to give you an idea what it means to do machine learning, right? At this level, at the system level, right? On the modeling side, Modeling is in general at the core of any design process. And for us, modeling is often one of the main challenges at high levels of abstraction, right? We often have applied previously machine learning in the past. Linear regression is nothing else than machine learning too, okay? But most of our problems are unfortunately nonlinear. So it's about applying advanced machine learning formulations to this problem. And again, on the optimization side, we want to do this for design time optimization or runtime configuration using typically some form of reinforcement learning. And a key aspect here is, right, there's a lot of work on IP reuse. The whole idea of using a reinforcement learning agent that I've shown here, right, is that we can take the same agent that has learned on enough designs and apply it to a new design, and we don't have to train it anymore. We can transfer knowledge from one design to the other, okay? That's the main difference to existing heuristics, okay? So rather than using existing pre-designed IP, we reuse knowledge, right, in the design process. And that's the premise that you have through machine learning, okay? Challenges and opportunities, I already mentioned most of these, right? We need to be careful about the appropriate learning formulations. Don't just throw a deep neural network at it, okay? We still want to encode human expertise. We have human knowledge. It would be stupid to waste it and throw it away and have a machine rediscover it, okay, painfully. Secondly, right, training set and selection and availability is usually a challenge, right? And then there's also the question of model exchange, right? I talked about the fact that systems are composed out of heterogeneous components. If I make an hardware accelerator, can I sell an ML model of my hardware for my hardware accelerator performance power prediction, right? We currently have IP marketplaces to resell System C models and RTL, right? But should they come with ML models that do predictions on top of it, right? In the end. All right. Any questions? Otherwise, I want to just quickly make a plug. As I said earlier, right, the second talk in this session, Giro could not make it due to visa issues. So he prepared a recording of the talk, of his talk on machine learning for high-level synthesis. The link is here. Here are a few teaser slides, right, for his work, but essentially very much similar challenges that I outlined already, right, even at the high-level synthesis level. We have, right, the problem of slow design time exploration cycles going down to synthesis and the problem of making estimates at very early design stages at C, C++ level. And again, applying machine learning to both of these techniques, right, in the end for, right, early prediction. And we'll hear more from Lisa about this, right, early, right, performance power prediction, in this case from C code or from RTL code, and then, right, some form of machine learning-based, reinforcement-based engines to explore the design space. In high-level synthesis, this means particularly setting the pragmas that every HLS tool today requires, okay? How much loop pipelining, loop unrolling do you apply, data partitioning, and all of these questions, can this be automatically figured out by an agent, right? And again, here's the link to his talk. I don't think it makes sense to play back a recorded talk here. There's nothing more boring than that. So you can get the link and watch it yourself, right? And we'll make that also available. Okay, so I'll leave this up here. Any questions?
So I have a question. So for your talk, so thanks for the presentation. So you said that using a neural network is out of the picture because of the overhead. So did you investigate on one of your work for a particular problem? What will be the difference? So because using neural network also can be accelerated by the neural processing unit. So
yeah,
this has a disadvantage.
I'm not saying it's completely out of the question, right? There's works that have applied deep neural networks to, for example, for RTL power and performance estimation. I don't know, we will talk a little bit about that, right? It depends on your setup, right? If you have the training data, fine, right? And then if you can afford the overhead, or if you have a way to accelerating neural networks, right? Yeah, so, but I'm making the point, you need to be careful, right? Not just randomly throw neural networks at everything, right? There's other forms of machine learning out there, right?
Yeah, sure. Thank you.
If that makes sense, right? All right. If there's no more questions, did you get your presentation on here now? So let me introduce the next speaker. Next speaker is Lisa Wu Wills. She's an assistant professor, right, at Duke University. She's worked before in industry, right, to some extent. So So you'll be talking about RTL synthesis and machine learning at that level of abstraction, in particular, right? Early performance power prediction from RTL descriptions, right? And essentially trying to predict, right, the behavior of the synthesis tool. That's what we're talking about here. So
Thank you. Thank you for the intro, Andreas. Hi, my name is Lisa Wu Wells, and I'm an assistant professor, as Andreas said, at Duke University. And today I'm going to tell you about one of our latest projects on leveraging AI for hardware design. And unlike Andreas' presentation where he has like all these publications, there's only one publication so far for this line of work, and we have a second one coming in micro, so which I'll give a plug in at the end. Okay, so the main motivation for using deep learning to expedite the hardware architecture design process is that synthesis is slow. So let's look at one example. So let's say we have an idea of an accelerator, and we want to figure out the best design for the workloads. Oh, I think I need to do, okay, for the workloads that we care about. So we start with a base design of, let's just say, a simple 32 by 32 systolic array, okay, that supports 32-bit floating point data type. And for each of the PE, we'll just say there's a multiply accumulate unit, okay, in each of the PE. So now let's say we want to know what is the estimated timing power and area to figure out what design decisions we want to make next. So we run synthesis using, let's say, Synopsys design compiler. Unfortunately, it takes about 1 day, okay, just to run the synthesis flow. So then let's say, oh, what if we wanted to try a different data type for this systolic array? Run more synthesis, okay? And then after this, let's say, oh, I don't know what systolic array sizes I wanted. Okay, run more synthesis. Then if we wanted to augment the systolic array PEs and see what impact it has on timing, area, or power, run more synthesis. Unfortunately, the traditional synthesis toolchain is so slow, in fact, that it makes doing any reasonable design space exploration, especially for larger designs or more parameters or higher dimensional DSCs, using these estimated physical characteristics nearly impossible, okay? So if you wanted to have a design target of using performance per watt or performance per area, you would actually need to be able to run synthesis, or at least be able to estimate what those physical characteristics are in a reasonable fashion. So this is motivating that we need to have synthesis predictions that are fast and accurate, okay? So our approach is actually to use deep learning-based method to quickly predict an arbitrary hardware design's physical characteristics, such as its timing, power, and area. So we use a graph intermediate representation we call GraphIR to represent a design, and then extract circuit paths from the circuit graph using a modified transformer model we call circuit former. And we use the circuit former to predict circuit path characteristics. And then we finally use a multi-level perceptron to aggregate these circuit path information and to obtain the attributes of the entire designs. So today's talk, I'm gonna offer a more detailed look at this, our approach. And the synthesis predictor is called SNS, and it's actually published at ISCA last year. So there are a lot more details in the paper if you wanted to read up on it. Okay, so for the first step to predict this synthesis results is we're gonna obtain a graph intermediate representation of the hardware design. So here is a hardware description language of a design that contains just one multiply accumulate unit or a MAC unit. And we use actually open source HDL compiler toolchain, Yosys. And we only use it for parsing and compiling the input design source into its circuit representation, which includes all the basic functional blocks and then wiring connections. And we use a GraphIR generator to construct all the input and output ports as well as functional blocks and units as vertices. Try to use it. Okay, so here. And all the connections between the vertices are actually wiring connections. So besides use the type of node such as IO or mul or add as an attribute for the vertex, we also use the width, okay, the bus width, such as here, IO8, it's an 8-bit input. So in this example, there are two 8-bit inputs, A and B, right? And then there's a 16-bit multiplier, a 16-bit adder, and then a 16-bit register, which is a D flip-flop. So you'll see DFF as ACC, and then I'll put 16-bit values C. Okay. So the graph IR representation allows us to sample these paths and perform graph analytics to obtain hardware design attributes. So instead of sampling a design, path in a design, beginning and ending at any node, what we're going to do is we're going to actually sample particular circuit paths, what we call complete circuit paths, that begins and ends with an input port or output port or a D flip-flop of some sort. So these paths essentially approximates the one cycle behavior of a design, okay? So that makes it possible for SNS to predict the timing, area, and power of these circuit paths and then gradually entire designs. So here we show 4 example paths. I'm going to go through the first one, which is marked in red. And here is the path goes from IO8, mul16, add16, and DFF16. Okay, that's one path. So you can see similarly, there are other paths like in yellow, in navy, and also in blue. So the type of the node concatenated with the width forms a token or a vocabulary that we're going to use to train the predictor in the next step. And it's not necessary to sample all the paths of a hardware design exhaustively because lots of the paths are similar and they don't give us additional information. And we use a depth first search based algorithm to randomly sample a subset of the complete circuit path to form a path level data set for training the predictor. And more details of the sampling methodology is in the paper. Okay, so once we have the sample circuit path, we want to now use a predictor to predict the physical characteristics. So the simplest and the most intuitive model, which Andrea had kind of mentioned, is a linear regressor, even though there are a lot of characteristics that's nonlinear. But in this case, let's say we just use the linear regressor, okay? So then we count the each type of the vertices on the circuit path, right? Then longer circuit path will have what? More vertices, and more vertices will have what? Larger area, larger power, longer timing paths, okay? So what's the problem with that? Well, for example, if there is a path that contains a 16-bit adder followed by a 16-bit multiplier, the synthesis tool chain is going to synthesize this into what? 2 separate modules, okay? Which is an adder followed by a multiplier. However, if we have another circuit path that is a multiplier followed by an adder, the synthesis tools are smart. So what they're going to do is they're actually going to synthesize this into one fuse multiply add module. So now for a linear regressor, it's going to count the number of vertices and the types, and they're going to say, these 2 paths are exactly the same. So I'm going to predict them with the same area, power, and timing, when in reality, it's not accurate, right? And there are actually thousands of these paths, okay? So we cannot use simply a linear regressor. Instead, we have to use a smarter predictor that actually takes into account of the order and the placement of the functional units in relation to other functional units, okay? So for that reason, we are going to leverage a natural language processing model because they are designed to learn the ordering and the placement and the relationships between words, okay? So each of the word is a token. And making these kind of models good candidates because we can see the circuit path as being a sentence that has all these functional units in different order and placements. Okay, so we formulate this circuit former, which is essentially a very trimmed down version of a BERT transformer from NLP. And we use a much smaller vocabulary size. And as I have mentioned before, the vocabulary is basically the type of the functional unit plus the width. Okay, so let's say for this initial version, all we did was if you had a bus width of like 5, we're gonna say it's a 4. Okay, so whatever it is to using a subset of the vocabulary in order to train this model, we're not gonna give it a huge vocabulary, because if we did, it would take forever to train and we don't have the data set, as Andreas has mentioned. Okay, so besides this, rather than trying to understand that each word or each functional unit independently, this model circuit former is actually going to understand the relationships between words and pay attention to adjacency information, ordering of the tokens, and also the frequency of the tokens to obtain a much more accurate model. Okay, so one insight of using a path-based approach as opposed to a graph-based approach is that the path lengths of hardware designs do not vary that much between small and large designs. So the state-of-the-art approach right now, besides this one I'm talking about, is usually GNN based. Okay, because it allows you to predict power very accurately and all these other physical characteristics very accurately. The problem with that is it doesn't scale. Okay, it takes up too much memory, or it encounters significant slowdown when you predict very large designs. So with this path-based approach, we are able to scale. And another advantage of using path-based approach is that it's much more efficient and less time consuming when we have to generate this ground truth training data set. Because all you're doing is you're actually synthesizing just paths, okay? Millions of paths or thousands of paths, right? And you can do them in parallel. So lastly, our predictor scales will, to quickly produce inferences for hardware designs up to 18 million gates. That's the biggest design we've done, but I think from the scaling, we can do much larger designs, doesn't take too long. So the other prior works, they have published maybe predicting designs up to 50,000 or 100,000 gates. Let's see. With the chips having more gates and also getting more complex, the scalability is actually necessary for future chip developments. All right, so another novelty of our approach comes from the insight that paths are actually sequences. So we can not only just leverage the NLP sequence predictions, we can also exploit other sequence-related models or processing techniques, such as using the generative adversarial network for sequences, or SeqGAN. Okay, SeqGAN, we can learn and generate new, unique, and complete circuit paths that are similar to the paths that sampled from the real hardware design. And this approach is going to address the data scarcity problem due to lack of open source hardware designs. Okay, so in total, we were able to sample around 700 complete paths from real designs, and we were able to generate about 3,000 of them using SeqGANs to greatly improve the accuracy and the robustness of our predictor. Okay, so having extracted these high-level features from individual circuit paths, now we can aggregate these results gradually into the prediction for the input design as a whole to produce these global inference results. So we use a simple multi-level perceptron model to aggregate the path level characteristics to predict power, area, and timing. So for example, to obtain the timing of a design, the critical path is the slowest path. So we basically use the aggregation function of max, okay? For area, since the path samples are evenly distributed, the expected area of the design is proportional to the sum of the area of each circuit path. So for area, we use the sum aggregation function, the same as power. So more details about the MLP model and the training data set can be found in the paper. Okay, so now that we have the predictor, let's evaluate if this predictor is any good. So I'm showing the prediction results here. we perform an experiment where we train and we evaluate our predictor using the training set size of 50% and using the other 50% as testing set. So the prediction accuracy results are obtained using a twofold cross validation, where we split the data set into A and B, and we will have the model train on part B, train on A, and then evaluate on B, and vice versa. Okay, so the y-axis here plots the SNS predicted physical characteristics, while the x-axis plots the synthesis results produced by Synopsys DC. And the closer the predictions are to the diagonal line of y equals x, the better the predictions. So to further evaluate the predictor, the robustness actually, when training data is even more scarce, we performed another experiment by using only 30% of the data as training data set and see how our accuracy fares. And we use the metric MAEP, which stands for mean absolute error percentage, and lower is better. So from here, you can clearly see that when you have more data, your model is a lot more accurate. And by the way, in the paper, you'll show that our accuracy is better than prior work. Okay, here's another result plot, but this time I'm not talking about accuracy. I'm going to talk about the speed up compared to the Synopsys DC. So on the y-axis, it plots the runtime of our model in log scale, and on the x-axis is Synopsys DC runtime in log scale. And the runtimes are measured wall clock times on a dual socket 48 core Xeon Gold server. So each of the design point is represented as a circle, and the area and the complexity of the design are proportional to the size of the circle. So bigger, more complex, and larger designs. And the speed up range from 10 to more than 5,000, with the lighter colors represent more speed ups. And you can see that on average, our predictor runs about 760 times faster. And the larger the design, the more speed up we can obtain. And the largest design we have run, experimented, is the 18 million gate one, which is the one in the yellow. In the very light color here. I don't know. And it's a 16-core accelerator for computing 2D stencils. And this design's physical characteristics are predicted in about 20 seconds, when Synopsys DC took around 2.5 hours. Okay, so one of the strengths of SNS is its speed, and also so then the natural use case is to enable a large and high-dimensional design space exploration in order to select the best designs that meet either a performance goal or a power area efficiency goal. So we choose to use a reasonably complex general purpose core to as a use case. So we use the Berkeley RISC-V out of order core to perform a DSE using our predictor. Synthesizing a typical Bloom core takes around 2.5 hours on a 16-core Xeon server. So we vary these microarchitecture parameters, such as the branch predictor type, the core width, the memory ports, instruction fetch width, physical integer, register file, ROB size, issue slots, L1D cache, data cache ways, and such. And we searched through around 2,600 designs to find Pareto designs. And here I'm showing the results of our DSE with around 2,600 designs. We plot the performance on the y-axis in core mark score, and then the area and power on the x-axis. So we selected a best performing design here, and then an area efficient design and a power efficient design. So the exact configurations are listed in the paper. And this DSE took around 2.1 hours to complete, when if you were to run a 48-core Xeon Gold server continuously, it would take about 45 days. So this use case showed that the predictor can be used for rapid development of complex hardware designs and sifting through thousands of designs in a matter of minutes to hours instead of days. And once you did this DSE, let's say you have a handful of designs that you want to explore more and you want to tape out some of them, you can then run the traditional synthesis tool chain through it. And now you only have maybe, 3 to 5 designs you have to run that through. Okay, so this is my last slide. For the last slide, I'm just going to briefly review some of the novelties I talked about of this work and then talk about its significance and future work. So we were able to exploit natural language processing model, the transformer model, to predict circuit path characteristics. And our circuit former uses each node in the circuit graph as a token and the circuit path as a sentence to predict the physical characteristics of a design by learning attributes of these circuit paths, not just from individual functional unit, but from complete circuit paths. And this path-based approach not only allows us to use augmented NLP model to predict hardware design attributes, it also allows us to provide scalability to predict large arbitrary designs. In addition, we were able to exploit other sequence-related models, such as the CGAN, to generate more training data in order to combat the data scarcity problem. We're currently looking into how to predict other physical characteristics, such as dynamic power. We're also looking at portability and transferability of a model. So the significance of this work is that to broaden these accelerator adoption and also expedite accelerator innovation, especially in the modern embedded system development where accelerator-rich SoCs are commonplace, we need to significantly simplify the design and deployment of accelerated systems and improve the ecosystem. So this predictor allows ultra-fast and also automated DSE of complex designs with large parameter space. And eventually we want to be able to speed up the whole hardware design process as a whole. And this is just one piece of it. So as I kind of mentioned in the beginning, our latest work is SNS V2, and it's going to be presented at Micro. And what we're able to do is to pre-train one model on one technology node and then predict across technology nodes. So we don't have to retrain the model every time when you have a different technology node. And thank you. I will now take questions.
Question for the new work.
Yeah.
What type of approach do you use? Transfer learning or?
Yes. We use transfer learning and we use the NLP 3-phase, which is pre-training, fine-tuning, and then domain adaptation.
Okay. Looking forward to it.
Yeah.
Any other questions?
Okay.
Otherwise, let's move on and we can keep some questions for the end for all of us. So let me introduce our next speaker. Our next speaker is Wolfgang Ecker. He's a distinguished scientist at Infineon in Munich, and he's also a professor at TU Munich. So he will be talking about industry perspectives on using machine learning for system design, in particular pitfalls and challenges, I think, about modeling and other aspects that we've seen so far in this session. So without further ado, Wolfgang, the floor is yours.
Thank you. Thank you. Okay. Yeah, we still are in the synthesis area down to, yeah, let's say closer to transistors, to electrons, to engineers. And also we try to speed up our design process, make things faster, more predictive, and also with machine learning to get there. Now, why this is not working? This is the end. I just get to the first or last one. Okay. Yeah, what I'm talking about, give you some introduction. I'm talking about a RTL generation framework because we heard here, where do we get data from? Yeah, and we use this framework to make a lot of variants to get trainings data, but also we want to use the trained data to make a pre-RTL optimization, where I would say synthesis tools are quite weak at the moment, to come up with a better quality of RTL code at the end to come up with a flow. I will elaborate on the synthesis flow parts you have heard. I will add some parts, and then I will report our results on machine learning based timing estimations, where upfront we follow a bit different approach with our reasons and our motivations. At the end, I come up with some open challenges, opportunities. So let's see. This is, I would say, a classical design flow. What is the, this one? A classical flow with a specification, RTL design, and then we have a lot of steps: logic synthesis, flow, and power plan placement, clock tree synthesis, and so on, routing. And after all the steps, which are depends on the chip, between a day and weeks, we finally know if our chips works or not. And especially these guys, where we call them the red eye guys, because we have to use any second of compute time to fix things which come up after a long run. That means even at midnight, morning at 3, at lunchtime, whatever, whenever tool is ready or analysis is ready, they jump on it, find a solution, and go on. It's really day and night job to get it done if you want to optimize. So the point is, is how can we get early information? How can we detect early that things don't go wrong? We have other approaches not presented today, which try to make congestions about routing, routability, also using machine learning, simply because that's an often underestimated problem, or also about hold time things. We also talk about performance and so on, which is propagation delay, setup time, but also with the scan paths, hold time is a big issue. Also here, we try with floor planning. I think you mentioned already floor planning and machine learning. We have another work going on. I'm addressing more here on this area, RTL design logic synthesis, but even there, if we don't know the clock tree synthesis, if we don't know placement, if we don't know the optimization, it's hard to know if my Verilog code is good enough or not. So therefore, we want to try to get information early in the design process. Also important is, and that's also why we take a bit of different approach. For us, it's not sufficient to make a prediction or analysis. We also need a feedback what we have to change. Where do we have, or automation, which is our final goal, reinforcement learning, pre-optimize my RTL code to come up with better results. And still today, the synthesis result is heavily QR, or the result is heavily coding style dependent. This is unfortunately, but easily, if you make an experiment, a CPU, ALU, make a hand optimization, you get 20, 30% optimized area over standard commercial synthesis tools, which is still amazing. Whoops, wrong direction. So this, I think, it was already described. You make a design synthesis analysis, doesn't work. Again, synthesis analysis, now I stop here. And what you want to do is you want to have an early PPA abstraction estimation. So for us, we only focus on timing at the moment, no power, no area. I think the area is relatively simple. I think tower is even more complex because it depends more on the pattern you also have to execute. So we are somewhere in the middle. As I said, our challenge is that the design meets constraints, many timing constraints. As also described already, back annotation timing to RTL blocks is challenging. It's a known technology. Doing something, annotate back and do it. You always have to go down to physics and then go up there for analysis. This is simply not affordable. So now, what do we do? What do we want to do is that we have somehow don't give me this stick. Okay, we have here a very simplified view. We can handle quite complex elements in estimation. We want to estimate the timing from A to C. Therefore, we have to estimate, or with our approach, we want to estimate the timing of the subblocks. When do a fast block-based STA, block-based STA is linear time algorithm. So we can run a talk that's easy. The good thing of linear time of block-based STA is that it gets slacks, and with the slacks we can identify critical components where we can do a range, whatever. We can do a chain tree transformation. We can do an arithmetic retransformation if we know where we have to start with. Now our generation framework, some words about it, simply as is described how we get to our designs and where we want to optimize. So what for our workflow is that we say, okay, we come up with a more formalized specification. That means we specify properties of a design which you want to have. And then these properties control templates, and with template generate code. In an advanced step, we do the same thing. We have a formalized specification. And now we generate an intermediate model, which is a bit up like your RTL graph notation. And again, we have here backend and dump code. Now you could imagine with this formalized specification, we can randomize them, we can build a lot of variants, for example, to generate our data set. This generation framework is based on a structured method from software called model-driven architecture. We have a specification in any form, XML, maybe text, whatever. You have to extract information. When you have your specification model, when you translate it to a design model, this design model, as I said, is an abstract RTL model. This design model itself, we have the classical thing which we have in RTL design, that's signals, pores, literals. So with the standard, we have standard components in there, but also complex components, yeah, like decoder tables, like FIFOs, like more complex things. And now with these basics components, what we have, let's say from an N2 gate to whatever highly complex sub-element or subject of the estimation for us, so that if we compose it, that we have with this block-based STA a fast feedback on our design. And at the end, we write out code simply because that's today's way how to come to your layout tool. You have to write Verilog or VHDL and go to a classical synthesizer or open source tool as we do it. The benefit of this generation approach, so we do not start with Verilog, we start with a generator intermediate, is that with this automation, we can produce a lot of variants. I think we have heard a lot of several times, we need variants for training. We also generate formal properties from this formalized specification, that we know what we are estimating is also the right thing what we are estimating. So that to say that the variant is still working. We have a RTL intermediate representation, which is a convenient data structure for LM algorithms, and we use Python in our generation framework, and Python is also the ML language, so I think we are at least speaking the right tongue here. The point here is, as I said, if we didn't consider or if we didn't build the right microarchitecture, also the generator produces suboptimal code. And also what's also important is the generators is billing by the engineer. So the engineer heavily relies on his stomach feeling, what's the right timing, and also feedback where to optimize is important for this overall generation process. So synthesis, what we use, this is also a reason for the design data. If we use this open source EDA tools, simply it's okay, or now with a generator, we can produce thousands, tens, thousands of variants, but to get the training data, we have to synthesize them. And if I go to my boss and say I have to run 1,000 synthesis tools in parallel, I think he doesn't like me. It's simply too expensive. So we use this with open source tools from the Open Road project to synthesize our examples and to get output. What we plan, not mentioned here, but as you said it, we also want to make a cross, so to say, cross correlation between USS results or Open Road results to our commercial design flow. So that to say that we can use this tool flow for estimation and then but so to say can somehow predict the timing of final commercially synthesized design. Why is this the case? Because our experience is, or we have published, is that with commercial tools you still get, I would say, some smaller and faster designs as with Open Road. But I think we are happy, very much happy that we have Open Road and can do a lot of experiments, plug in add-ons and make experiments and so on. So how do we do timing estimation? So what do we need? What I said, we do block-based STA. Block-based STA, as said, is linear time complexity. It's the shortest or longest path problem on a uncyclic graph. So this is straight, easy. So what do? We have random configurations. We generate those. With a generation framework, we generate the RTL code, and also we make a ground of truth. We know we extract the features. We have a dataset builder. We run all the synthesis reports. Oops. We have a ground truth label extractors from these reports. And finally, we have our training set. With this training set, we can train our machine learning models and have a trained model. Then with this trained model, we can apply it to estimate the timing of our sub-elements and then go with them to be designed. Okay, how do we represent the things? Which is also important, because if we want to learn something, how can we do that? We can do it in a tabular-based way or graph-based way. Tabulars are more easy, I would say, for classical machine learning. Graph data, you will see later, are better for graph neural networks for the prediction. So let's see. With the tabular data, we tried out random forest decision trees and linear regressions and also MLPs. And with the graph data, we tried out with graph neural networks in general, and especially graph convolutional networks. As I said, we generate the hardware, so we have an ability to produce a mass of data which is required to feed the or to train the CGNs. Also important for us is, remember that we do still the timing estimation, not for the complete design, but over the subblocks, the RTL subblocks of a design. That means for us, the graph convolutional networks are not that big as if you would consider a complete design. So what's the result in summary? You see also the publications. So long story short, the graph convolutional networks outperform all our models. You see here the figures, and also an important thing is what we tried is to have one model over all components and then have a second machine learning model to do the selection, or also feed the kind of model to the estimator and then estimate over design groups. What does it mean? We would have, let's say, a multiplier, an ALU, FIFOs, register files, all fed in the estimator, and when we tell the estimator, oops, what's this kind of thing, and when do estimation. And neither or either as a complete training set or as a training set of subsets, and when an additional neural network to do with selection, the results were not acceptable. So only when we started to train really circuit specific in a circuit specific way, we got this result here. And of course, using now the inference of the models is much faster when using RTL. Now the question is, hey, you're just having some blocks, why do you use machine learning? Yeah, because machine learning is a good application if you don't know exactly what happens. And what do we don't know? How the synthesizer is optimized, especially the boundaries. Yeah, if you wouldn't flatten boundaries between your blocks, it would be straight. Yeah, make your block and put them together and you know the area. But often the synthesis tool optimize over the boundaries, which then substantially change the behavior, time behavior, power behavior of the design. And since this is very hard to predict, machine learning for us was a quite good or successful tool for this early estimation. As the other speakers, I also want to talk about some challenges. Very important is, where do we come from? Yeah, we now, let's say, the world before machine learning and language models and the world after and before. I would say we tried to structure the world. Yeah, we had physical abstraction, lump model, gate, and so on up there, and we knew what we were doing. Yeah, between every step, we knew what we abstract and what did we do. And now over these 4 steps, we come up now with a machine learning approach without knowing what we are doing, because the neural network doesn't know something about some simplifications we apply if we come from physical abstraction, means Maxwell to lump, or if we come from lump to gate models. And that leads me to the challenges. We are used as engineers, as scientists, to introduce abstraction simply to simplify the world and to be able to handle complexity. Abstraction is domain and problem specific, but at least we represent by training. Yeah, by the kind of training, what we train the networks we select, we can represent it. But if you follow the statement of George Box, which by the way was a statistic or math professor or a scientist, he says all models are wrong, but some are useful. In the same way, also machine learning models are wrong. But we have now the point is that we can make models useful if they follow proper abstraction, if they are properly made and validated, and if they're used in the right way. And with a machine learning, we still are in this dust. We get some statistical information, so to say. We get some statistics which analyze this training process, and to, let's say, to some extent, what we're doing is okay. But we only have a statistical feeling about, or a statistical measure what we're doing. We never get a guarantee. Do we have really the worst case timing for us? We don't know it. We only get a statistical feeling. And this is something not mentioned here. Would be also nice to have some measure of confidence. How confident can we do what the network is providing to us? Yeah, what's a confidence factor of it? Now you're saying, why are talking about statistics and so on? Of course, our world is statistical. We live with it. We simply don't want to like to do it. We always would like to have black or white, right or no, fits or doesn't fit. But conceptually, the world is statistical and the design process is statistical. So the machine learning models, which have some underlying statistical nature, also tell us to some probability good results. And where you also see here, if you see here the figures, yeah, with R square, for example, is 96%. It's not 100%, it's not perfect, 96%. But now what does this 96% tell me? Yeah, how much confidence, what probability do I have that if I go on now with a design chain, will every 10th design fail? Will every 100th design fail? I don't know here. So this is for us really what I said, one of the biggest challenges how to understand what this machine learning, how useful it is abstracting for us and what is telling for us. I would say this is all covered. The future. Well, RTG said sooner or later we get a ChatGPT-like or generative network-like tool which synthesizes us with RISC-V. So we can close conferences, close all hardware design lectures. Interestingly, all Europe says more students have to learn hardware design. RTG says ChatGPT will do it. I wouldn't say, at least my stomach feeling is this was a bit advertisement, a bit provocative. As you have seen in our examples, we have to distinguish between the kinds of designs we are estimating to get acceptable results. And that's a real way where we are, and that we have a tool which makes us a RISC-V optimized in a way. Just by applying the ChatGPT technology, I would say it's a far way to go. We also need some explainability to get trust on ML, because at the final end, if you derive a design and we say the car will drive or the car won't make an accident, then immediately you are asked, and what's your confidence that your chip really fulfills the tasks? By the way, also safety is not a 100%, but a extremely high probability that everything works fine. Also important, what at least our finding is, machine learning cannot solve complex EDA problems, but if we have some solutions very targeted, what we have seen in all the talks before, system level optimization, power estimation, other things, then machine learning is a very powerful tool. And I'm sure that this will change the way how we do design, and how fast we can make new designs. Yeah, this is my final conclusion. Other questions?
Any questions for any of us, actually, but for Wolfgang specifically? You had one slide, you skipped over the ML models. You don't know what they're abstracting, right?
Yeah.
Yeah. Well, I think that's an important point. It comes back to the explainability question, right?
Exactly.
What has the model really learned? And that comes back to confidence questions, right? Especially if you use, I mean, in a regressor, I have a better idea what the regressor is doing, but in neural networks, who knows, right? When will it fail? That's the question.
What I try to say is, maybe we even don't have to understand what the model are doing. So maybe we can skip on understandability if we can statistically, that means statistically derive a confidence factor.
Yeah, and some models are able to do that, others
exactly,
are not, right?
Exactly. This is a big point. If you don't have a question, then I have a question. Who will use or want to use machine learning to design a chip? Hands up. Or software.
What was your question?
Who wanna use machine learning? Good morning, wake up, coffee is coming soon. Who wanna use machine learning to design hardware or software?
Who is using it?
Hardware or hardware software. So problems in the scope of a conference. Okay, which is about 15%?
A little bit more, maybe, yeah.
20%? The other 80%, reluctant, don't trust AI, or why are you using it? Or is it too complicated, or? Well,
there's no real tools you can get yet, right?
Yeah.
Worst case hypothesis, and this is the classic approach. Thank you. The classic approach has been for RTL and placement and routing that the worst case of timing, for example, dictates your clock frequency. So it's a not an average case or expected case business, but the worst case. And machine learning is, for the corner cases, it may not perform well. For the expected case, it performs very well. Can you comment or foresee, is that going to give it a challenge or a headache, or it's not a problem?
No, okay. Why are we doing that? Yeah, because we spend too much time. Yeah, we spend too much time here, praise the Lord. Yeah, this tolerance is enormous. It takes, what I said, days, weeks to get one design through it. And we are doing it to get this time down. That means to come up top down here with a solution which with an extreme high probability really will make it. We are not sure, maybe at the final end we find out our estimations were wrong, we have to redo it. But we try to get this down, this number of redoing down as much as possible. We never escape here. All the things what we do is layout rule checking, physical verification, classical STA, we never escape that. Yeah, because that's our guarantee to the customer, hey, our thing works. What we want to do is to come with a quite high confidence down there and say, okay, in almost all cases, we will make it. And for us now is the question, oops, wrong direction. With 96%, what does it say? Yeah, because we spent some effort. Yeah, all of us said, yeah, it's quite an effort to collect training data. Running the estimators is also not for free. Yeah, and reacting on the estimation is also not for free. Now the question is, what means 96%? Does it mean 96 of 100 designs will pass through and only 4 we have to rework? Or is it, what's the impact? That's what we say, what's the confidence, what we need in these figures to find out what is helping.
Yeah, I think a key point is also that I don't think, at least that's my opinion, machine learning will not replace traditional tools. It will complement them. It's a productivity enhancement, right? But that's actually one open research question. How do we combine machine learning with existing tools, right? In a reasonable fashion and in an effective fashion, ultimately. One more question. The microphone is coming.
My question is specifically about one of the slides where you talked about that we cannot trust the black box optimizations. Like if we have any sort of like more wider optimization like an ILP, should we actually limit on like could there be a discussion about that if we limit on the IP modules design itself, which would be more like a high level SoC design and not going within the routing and the STA part of things, because over there might be huge search spaces, but we have surrogate models like cycle accurate simulators, which can actually help us at least guide in the search space effectively that, okay, design choice A versus choice B. Maybe B is a better choice because for some reason it is optimizing on our performance models or has better thermal constraints being handled. And that could be motivated by any data-driven design methodologies, which might be a black box optimization, but on an IP module, we are not going within the IPs, which could be taken care by the engineer. So that could speed up some of the aspects of research within the field. That was the overall.
You want to answer? I mean, I think that's exactly the point, right? Especially at the higher levels of abstraction, where we have surrogate models, like you said, cycle accurate simulators and other things. These are inaccurate themselves, right? And I mean, that's what abstraction is, trying to find the best trade-off between speed and accuracy, but you never can get both, right? And the higher you go in level of abstraction, you make trade-offs, right? And yes, machine learning can hopefully push that out in these trade-offs, but nothing will replace having to go down for physical design at some point in the design, right? So it's about ruling out regions of the design space where that confidence that the model gives you is good enough to say this design will never work, for example, right? And you reduce it down, as we've seen in Lisa's talk, to a set of candidate designs that have potential to take them down further, right? And you have a funnel that brings you down, right? Hopefully you'll end up only one design that you take down the physical design. Likely not, right? But a handful maybe or so, right? Initially you start out from almost an infinite number of choices at the system level, right? So yeah. Yeah.
Compiling for a platform is that you have a compiler in between. And so you're trying to estimate the performance of your code running on your hardware, and then you have a compiler there.
Yeah.
And how do you account for the compiler, especially taking into account that in DSPs and most platforms, actually the compiler options in themselves are going to have an extreme effect on what is going to happen there.
Yeah.
And just to add one more thing, in typical embedded system development environments, we're constantly changing the compiler and optimizing it, which means that your system, whatever prediction you do, is probably going to be outdated the next day because your compiler is already doing a better job today.
Yeah.
So I would like to have an idea of how do you account for that and how you expect that actually to influence the way that you're going to do the design and include it in the
so you have to be aware, right? Especially at a system level, if you make models, right? What you're really learning is not just the target, you're learning the tool combination that produced the target, right? But when you make predictions for, let's say, mapping a code to an FPGA, you're making predictions about the high-level synthesis tool, the FPGA synthesis tools, and all that things that are in between, right? So you have to be aware that your target is the combination of hardware and the tools, right?
Right, but you have all these compiler options in between that are going to
so you every time you change, right, there's the tool flow, basically you need to retrain the model technically, right?
And technically every single application would use different compiler options, so those would have to be part of the training
so then
set.
the question becomes, right, you have two options, right? You can either retrain the model or you can make that option an input to the model and make it a feature and try to train the model to predict the impact of that feature.
But
right?
how complex is that?
Right? Question, right? How much of that you cannot make everything a feature, probably, right? It's a question, right? These are all open questions, right?
Yeah.
But I mean, ultimately, that's what we missed Shiro's talk. But in high-level synthesis, right? Modern high-level synthesis tools are really, right, a lot of the effort is still left on the designer to choosing the pragmas and the synthesis knobs and whatnot, right?
Exactly.
So these tools are trying to explore that design space, basically. But you need to have them predictions that given this knob, what will come out, right? So yeah, you need to train models that are aware of the knobs and the options, right? So
And how would you deal with the change?
yeah,
Because what I notice with compilers is that sometimes it just takes a little change here and your performance doubles
yeah.
for a particular load. So it feels like your search space is ultra unstable.
Yeah, so I mean, that's I'm not aware of any model that is trying to do compiler predictions, right? That's a good, interesting research question, I think, right? Can you predict the compiler, basically, right?
I think that's
impact.
pretty difficult.
So we've done our modeling mostly on the hardware side, right? Either for fixed function hardware accelerators or where we have insights from the high-level synthesis tools that we can extract and feed into the model, so the model knows, right, what's available, right? So yeah.
Thank you.
We did the cross-platform prediction where we predicted from software running on an x86 to software running on an ARM, right? Which included somewhat the effect of the compiler.
Yeah,
right?
so that I
But
know.
we assumed it's the same GCC, for example, right?
So that work I know that you can actually try to extrapolate, like you have training for the performance of 2 or 3 different
Yeah.
processors, and then you extrapolate
But
for
I'm
fixed
clear we would have used a different compiler on the ARM, we would have to retrain, right?
of
The
course.
model.
Yeah.
Like. It also interesting question, what does that mean about microarchitectures? Are they all the same if they're so easily predictable, right?
I don't think they are. I think most of the models I saw used very standard architectures, and if you start going for more exotic architectures, the model starts to fail.
Yeah.
So
Anyway, we can take it offline.
sorry.
right?
Yeah,
Have a
thank you
coffee
for
break.
answering.
Any other questions? There was one up here.
More in terms of applicability and limitations of these methods. Like generally, when you're designing circuits, you're going for something new, something more optimized.
I couldn't hear you. Can you speak up a little bit?
Oh, sorry. More in terms of applicability and limitations of these methods. When you're designing circuits, you're probably going for a new architecture or a more optimized design. Machine learning specifically is an interpolation method. If you just look at supervised learning, what do you suggest in terms of sometimes you would have to extrapolate out of what you have trained for?
Yeah, I mean, that's a question, right? I mean, Lisa was talking about it, right? if you make a synthesis prediction that's specific to one technology, right, you can try to apply, I mean, Lisa can maybe talk more about how that works, right? But you can try to apply transfer learning methods or so, right? To take the knowledge and transfer it out, but you need to have some sort of retraining, right? The whole idea of transfer learning is rather than retrain completely from scratch, you can take some of the knowledge you've learned from the previous design and use it for the next one. Yeah, but either that or again, the same question is can you make technology parameters an input to the model as features, right? But then you have to train over many technologies and try to hope the model can learn common factors that are common across technologies, or how much, let's say, right, the technology node size influences performance or power, right? And learn that. Machine learning ultimately can only learn if there is an inherent correlation, right? If there's no correlation between your features and what you're trying to predict, then you're trying to learn noise, right? Okay. So, and that's the whole point of feature engineering, trying to find features that are highly correlated with what you're trying to predict, right? And reducing it to only the features that are highly correlated and they are not cross-correlated, because then you have redundant features, and right, that's where the feature engineering comes in, right? And in the old day machine learning for image and video recognition, human effort was the most, right? Feature engineering, months, years of work, and then you had one finally fully connected layer that did the classification. We've replaced all the humans with deep learning, right, and convolutional layers that we can learn, right? Given that all the features and images and videos come from filtering the image, and we can learn a filter, right? But what does that is for EDA, right? What's the canonical representation? Or should we even do that? Again, we know a lot of things as humans. We know what's correlated to power, right? It has to do with switching in the circuit, and we can abstract switching as Hamming distances on the inputs, and right, that's going to be your features, right? We've already encoded a lot of knowledge there, right? Yeah, so, but yeah. Anyway, I don't know. I mean, supposedly it works, right? Transferring over technology, so there must be some inherent correlation between technologies, right? That can be learned.
Like, then that, versus there's another technology that you can be able to work.
Yeah, I don't know if you guys have experiences with that. Transferring timing predictions across technologies, for example.
Nope. I would say no, it doesn't work, because we even have let me explain. We even have to redesign.
Yeah.
We won't have a different core optimized, let's say, for 130 nanometer and for, let's say, 22 nanometer. It's different because the fraction between area of cells, the runtime totally differs. It doesn't scale equally over the devices you use to build a thing.
All right, I think we're officially out of time. We can move the discussion over to the coffee session, I think, right? We have a break now, right? Yeah. All right, so see you there. Thank you.
Danke fürs Organisieren. Ja, hat Spaß gemacht.